Without a blueprint, stepping into the 2025 AI landscape will waste months of your life. There are thousands of frameworks, libraries, and competing philosophies. The most common trap is trying to build from the absolute bottom up. People think they need to master linear algebra, calculus, and probability before they can even touch a neural network, much less deploy one. If you take that sequential route, you are staring at a 2 to 3 year learning curve. The burnout rate is massive, and by the time you are ready to enter the job market, the tooling has already evolved past you. The opposite trap is the copy-paste approach. You skip all foundational math, grab a tutorial, and start importing libraries to build a quick application. You will get an app running in a weekend, but the second your model hallucinates or your inference costs spike, you will have zero ability to debug it or optimize performance because you don't understand the underlying weights and biases. This chart shows the decision you must make. Path A is the researcher, focused on building the engine itself, deep mathematics, and designing entirely new model architectures. Path B is the AI engineer, wiring those research engines into scalable products using MLOps. Choosing a specific side of this dichotomy determines every tool you actually need to master. Without that target, you are gathering skills for 2 different jobs. We are going to walk through the exact blueprint for identifying where you belong. Let's break down the first major dividing line in the landscape, the foundation layer. This is where you decide your ratio of mathematics to practical coding. The traditional academic route relies entirely on linear algebra, calculus, and probability. If you are on this path, you are living inside texts like Goodfellow, Bengio, and Corville's deep learning. To actually do this right, you have to dedicate 2 to 3 solid months doing nothing but studying those mathematical concepts. The return is the ability to read state-of-the-art research papers the day they drop, and to write custom loss functions entirely from scratch. But for an engineer, that level of mathematical depth is a massive time sink. For 80% of standard business use cases, like routing customer support tickets or analyzing sentiment, it is complete overkill. If you want to invent new AI capabilities, mathematical rigor is mandatory. If your goal is simply to deploy existing intelligence to solve a business problem, it acts as an unnecessary roadblock. This matrix illustrates our second pillar, selecting the right architecture and software framework once your math decision is settled. Looking at the tooling row, the academic side requires inputting heavily into low-level dynamic frameworks like JAX or PyTorch. These give ultimate flexibility. You can define custom convolutional neural networks and construct complex models to your specifications. The cost is a steeper learning curve and the manual burden of writing and handling your own training loops. On the engineering side, you lean on high-level APIs like Keras or Hugging Face transformers. With these tools, you can deploy advanced vision or natural language processing models in just 10 lines of code. But that speed means you are locked into pre-trained parameters. If you need to alter the underlying architecture of the model, you are going to struggle. Those limitations become obvious when you hit specific architectural challenges, like dealing with sequential data using recurrent neural networks or LSTMs. While RNNs capture time dependencies highly effectively, they are notoriously difficult to train compared to standard networks because of the vanishing gradient problem. Ultimately, your choice of framework dictates your daily job. You are either configuring parameters to get a product shipped, or you are writing custom architecture logic to push a metric. The third pillar is where the reality of the industry hits. Training a model is only a fraction of the work compared to the production tax. To bring a model out of a notebook and into the real world, you have to invest heavily in MLOps, infrastructure tools like Docker, Kubernetes, and MLflow. This yields highly scalable, monitorable systems. But the trade-off is that you spend your days learning traditional DevOps instead of building actual deep learning models. And once that system is live, you immediately face the ethical and legal liabilities of deploying AI into production. Responsible AI requires mandating diverse training datasets and building strict human-in-the-loop oversight checkpoints directly into your workflow. These steps mitigate algorithmic bias and legal accountability. The downside is that they drastically slow down data ingestion and drive up your operational costs. A deployed enterprise-grade AI system is only 10% deep learning logic and 90% engineering and compliance wrapper. This scorecard maps your tech stack. Absolute beginners focus entirely on APIs, like Keras and Hugging Face. You'll build projects fast, but fail technical interviews. AI engineers learn 20% stats, 40% PyTorch, and 40% MLOps to bridge research and product. Finally, we have the academic and researcher path. Your required input is mastering the Goodfellow textbook, writing in JAX, and understanding advanced calculus. You will be equipped to push the boundaries of AI capabilities, but you will spend years working in pure theory before you ever see your models in the hands of a consumer. Modern deep learning has fragmented into a series of specialized roles on an assembly line. True success requires picking your specific station on that line before you commit to your first month of study.